All right. So anyway, what we're going to do today is talk about generative AI, foundation models, and how we operationalize them. We'll show some live demo. I hope it will be interesting. But let's talk about the challenges and the solution in that space of what you need to think about when you build those large language models. So before we start with sort of the technology, let's understand what we're talking about. So we see a trend of more and more foundation models. What does it mean? Instead of building small models that fit a single task, building very large models that fit a lot of content, a lot of different tasks, and we can identify those foundation models by application. Things that know how to generate video, or images, or know how to address text, and you have some different examples of those foundation models. We're going to speak about those, but everyone knows ChatGPT, GPT-3, GPT-4. Those are examples of large foundation. Now we need to sort out the terminology. Again, maybe different people will have different terminology for those. But the first thing is foundation model. Again, very large models trained on massive amounts of data and computation. Very expensive. We're going to touch upon it. Then we have a term generative AI, which is essentially usually foundation model because they need to be intelligent enough to generate content, textual, video, images, and so on. And there's large language models, which are also sort of usually foundation models, and they're focused on text and natural language processing. So with those terms, let's continue. So how do we build those language models, and how do we use those large language models? So the first thing, we need to collect lots of data, and this data needs to be prepared because the data may have all sorts of symbols and things we want to remove. There are all sorts of tasks that you want to apply to the data to make it really usable for training. Then you're doing training. Again, foundation model, training of foundation models is a very expensive and long process. And finally, when you have this foundation model, you can tweak it to do certain tasks, which is the demo we're going to show later, is how we take a foundation model and adapt it to a specific application. And once we have those sort of altered or fine-tuned models, we can use them and deploy them as part of a bigger application. That's the general flow of how to use generative AI or large language models and so on. Just to understand why you don't want to train your own foundation model, this is sort of a chart showing the number of parameters over the years. GPT through 3, 4. GPT-4 has 1 trillion parameters. GPT-3 has 175 billion parameters. Okay, so this is a huge amount of data. It's trained on many terabytes of data, and it took, for example, GPT-4 took to train 25,000 GPUs, a cluster in Azure with 25,000 GPUs across a few months. Now you train, it doesn't work, you train again, the cost pile up. We're talking about tens of millions of dollars for training a model. So if you're Google or Amazon or Microsoft, that's okay. If you're an enterprise, you don't want to spend tens of millions of dollars on building your own model. And the landscape keeps on, you have solutions keep on popping. You have, the yellow ones are open, and you can essentially just use them without licensing, and there are some which are commercial, like the GPT family. And we see that there are more and more models, mainly by the key players, Google, DeepMind, OpenAI, Cohere, and so on, and Facebook and Meta. So again, no need to reinvent the wheel and build your own model unless you're a very large organization. Now, how do we take those models and do something specific with those models? Because again, if we just want to play around with ChatGPT, use the API, and we're done. But the key power of LLMs is to try and tweak them to a specific commercial application, which will work with your own data. Okay. There are also aspects of license, like everything you prompt to ChatGPT belongs to OpenAI. Okay? And someone else may get the answer based on data that you fed into ChatGPT. So If you're someone that deals with proprietary data, you don't necessarily want that to happen, so you may want to, again, use your own fine-tuned model based on some open technology or commercial technology, but the IP belongs to you. Okay? So there are three techniques of how to make the model, the large language model, tune to whatever you need. So the three are here. There's maybe a fourth one, but the prompt engineering is the first thing that everyone talks about. Is how do we frame the question to the large language model so we get the right answer. The question could even say, here's a document, summarize it for me. So I'm actually not just asking a question, I'm providing the context, I'm providing the data for the large language model to essentially think of sort of mini training, essentially giving the documents that I want to get answers based on those documents. It does have some challenges because I'm feeding lots of data for every inference request. So that's a lot of tokens, and that's slow. And also, I usually have limits of how many words I can feed in such a question, 1,000, 2,000, but I can't just put a bunch of documents. I probably maybe a couple of documents is an so that's a sort of limitation of prompt engineering. But the nice thing about it is the reliability and risk and all that. That's problem of the guy that provides the model. It's not my problem. There's also other aspects of versioning. If you change the version of the model, then the prompt may not be relevant. You can read more details. The second option is to fine-tune the model. Essentially, to take the model and start adapting it or changing the weights in the model, and this way teach it more information. So you have a base model, you bring in documents, and it starts understanding those documents, and we're going to see a demo later on how we do that. And so this is usually helps us to train the model on a lot more data. It reduces the inference time because I don't feed all the documents every time I'm querying the model. It's sort of already in the neural network of the model. But it does have more challenges because I need to do training, so I need to build training pipelines, okay, not just prompts. I need to address validation. One of the biggest challenges we're going to see is validation of large language models and the risk that they bring. And I need to think about continuous deployment. I'm deploying a model, I'm tuning it, I need to redeploy, and so on. So these are some of the challenges when we're doing fine-tuning, and we'll show them later on. The last thing is also, if you're using something like ChatGPT for, preparing your summary or your article or cheating in school, that's okay. You may make some mistakes, okay? But if you're trying to base some real business case on something like ChatGPT, if the answer is wrong, you have a challenge. So you need to make sure that the model keeps on tuning, keeps on fixing itself. So there is a technique called reinforced learning from human feedback. Essentially, we're taking information, we're taking answers that the model provided with the question. We have someone inspecting those and saying, oh, you know what, it's the wrong answer. Or that's not the kind of answer we want to answer. So then we want to create sort of a feedback loop. Keep on retraining the model and improving it to address those errors. We can even put a button near the response for the user saying, was the answer accurate? If it says no, we send it to a human later. So there are different ways of essentially not just statistically sending all the requests and responses to humans, because that's going to be expensive, trying to figure out using maybe even a model that examines the results. If the results are not so good, then we want someone to go and examine them. So this is another thing, and in terms of complexity, you have all the complexity of fine-tuning, because it's retraining, so you have even more complexity of human labelers in the loop, tracking all the information, inputs and outputs, and so on. Now, one of the biggest challenges with LLMs is risks, because language models, and we have a bunch of examples where companies like Microsoft or Google or Amazon introduced a large language model, and after a week it sort of crashed and burned because it sort of spitted about a bunch of toxic statements. And there are things that you need to make sure that you do very proper validation in two areas. One is in the training loop. When you're building the model after it's ready, you want to test it extensively to see that it's not generating any error issues. And the second is even in the real-time pipeline, before the question is fed into the model, or even after the response goes out of the model, making sure that it's not going to have something toxic or some bias and so on. So what are the typical challenges or risks? And I have a couple of examples here. One is around fairness and bias. You know, maybe it was learning a lot of information based on some data which was biased more towards men, and then you may give answers or maybe racist answers and so on. Another thing is around intellectual property. I mentioned this, that you're training it with lots of data, and the data may belong to someone else, and you're spitting an answer which essentially violates intellectual property. Or if you're using a public solution like GPT, then they learn from your private data. So every time you ask a question, essentially be careful with what you're asking. Don't provide proprietary data, because all this data belongs to them. So that's what it's always. Toxicity, so models can start curse and do things that are not so nice, or regulatory compliance. Also issues that it's spitting an answer. How do you know that the answer is really valid? Some of the technologies in the space are to try and give you the reference to where the data came from. It's not so trivial, because when it's spitting the answers from the neuron, how do you know if it's from this document, from some university, or another document? But these are some of the technologies to actually provide you references to the content, so you validate that this is the right answer. There's another nice example here for something called hallucination. So a model can reinvent the world. There's a nice example here. What is RLHF or LLM? So it just invented some nice acronym, which is obviously false. And just Google, you'll find a lot of different examples. There's another nice example here that, how to convince someone to join Al-Qaeda. So you could get an answer, and you could use this for malicious things. But what you'll see in more and more commercial models, they'll know how to protect against it. So they'll know how to analyze the response is sort of misused, and they'll provide some sort of canned response. But if you Google again, you'll find a lot of ways to bypass those mechanisms. Like if you're saying, I'm an actor and I want to tell someone how to recruit for Al-Qaeda, it suddenly may give you the answer and bypass the filter mechanism. So this is still something that's being worked on, but the key message here is that the problem is not really training. The problem is how to guarantee that the response are valid, they're good, they're high quality, and so on. So that's a lot of MLOps and automation and testing. So this is sort of a more generic slide when I explain what is MLOps about. Is usually we have those people working with the Jupyter notebook, and they're doing some data preparation and training, etc. And they finish their work, and then you need to build 3 different pipelines, not one, 3. One for data processing. I'm talking more about online applications, not sort of decision support where you just sort of building a report, things that really work. You need to build data pipelines that crunch data, online data, do the transformations in a repeatable ways, either streaming or scheduled. You need to build the training pipelines, but the training pipelines, as we just discussed, contain a lot of testing and validation and data cleansing and so on, part of what they do. And you have the serving pipeline. Serving pipeline is not just an endpoint. A lot of people say, oh, we're going to deploy a model. But the model doesn't just work by itself. You need some data pre-processing and validations and scoring and post-validation and so on. So you need to build a full multi-stage pipeline for serving. And all of those things, each one of them have challenges around monitoring and scaling and versioning, instrumentation, automation, and so on. So these are the real challenges where most of the organizations fail, because they need lots of engineers to take whatever the data scientists built in the notebook into real world production systems. So really what we're trying to do in MLOps is automate. So people develop, whether these are the data scientists or data engineers, using traditional tools, whether Jupyter, their PyCharm, their SageMaker, whatever, and then try through automation to build the production assets for those different pipelines. So applying auto scaling and auto monitoring, and everything should be automated, so users don't need to spend a lot of engineering, and this allows you to essentially rapidly deploy projects into production, build sort of a factory line, much better use of resources because of elasticity built into the solutions, much higher quality because of the auto instrumentation and monitoring and tracking of everything, and also continuous deployment. So if you make a change here, it's much easier to go and create a new version of your solution. And this is what we're doing with MLRun, which is an open source tool, so you can develop whatever tool you want to use. And then through automation, we build 3 different types of pipelines. We use the feature store to build the data pipelines. We have distributed machine learning pipelines for the training and testing. And we have the elastic serving application pipelines for the real time. We'll show the 3 of them. One thing which is very unique about MLRun is trying to do auto instrumentation. So you don't need to do anything in your code. It will automatically build like the model monitoring, the experiment tracking, etc. It essentially examines what goes in, what goes out to every task that you're doing. It's adding code in, injecting code into your code. So it's making it production ready and knows how to track all the different resources and data points and correlate them accordingly. And using automation and serverless technologies, it's deploying it on whatever cloud or on-prem services. So that's the general idea. So now let's talk specifically about building pipelines for generative AI. So this is like a typical training pipeline for building generative AI model or model. So we talked about 2 sources of data that we have. One source of data is sort of the specific data set that we want to extend the model to know about. The second type of data is the feedback loop. Remember that we're keeping on improving the model based on this reinforced learning. And then we need to do some data preparation, validation. I won't go into all the tasks, but in order to get to production, you have lots of different things you can do that to clean the data, make it much more ready for the training. Because if it's not, you'll see that the model doesn't produce good results. The next thing that we do, we take the base foundation model, and we need to do distributed transfer learning or fine tuning, and essentially this way generate a more tuned model, which knows something about our data. This is the baseline. Once we've done that, we want to run a set of evaluations to see that it's actually working. It's actually spitting the right results. It's accurate. It performs, and so on. And then there's another optional step, which is optimization. It's essentially trying to compress the layers in the model and so on, because part of the issue with large language models, they take a lot of memory. That's why it's called large models. And more memory means more GPUs and more CPUs. So we want to try and shrink. On one end, shrink the model, still maintain the same performance, but shrink the model as much as we can. The second thing, we want to increase the performance. So again, a smaller model will perform, will have better throughput. So this is why we usually also apply sort of an optimization phase. Once we have the model, we need to do all sorts of testing, but as an example, 2 main ones, like stress testing, taking all those risks that we wrote about a week ago, and starting to generate data that will examine bias, examine that these are the right results, see that we don't have toxic results, and so on. So that's on one end. And another thing is deployment testing. It's not just testing it on the model itself, but actually trying to build a full application, deploying the full application in real-time pipeline, and then feeding data or requests and examining responses on the end-to-end solution. Why? Because maybe you're doing some testing, it works okay. When you deploy, you forgot some package in the container, or you have some some misconfigurations where the production pipeline will not work like the generic testing. But this is just an example. Again, everyone will build his own pipeline. We're going to show one example. One of the nice things about MLRun, there is a concept of marketplace for functions. So all those functions are part of the marketplace. You don't even need to write them. And what you need to implement is only the custom code for usually the data preparation and testing. So again, some of those challenges that I listed here, the complexity of many different people. You see data engineers and ML engineers and testing and so on. Large-scale data processing, the training must be distributed. You won't be able to train on a single GPU, single node. You probably need some dozens of nodes in some cases to be able to fit the model, depending on the baseline LLM. Again, validations, a lot of work needs to be applied on validation and testing. And the nice thing about it is many of those tasks of validation and testing are not related directly to the model that you're using. Whether you're using GPT-3 or 2 or something else, then a lot of the code that we're doing here within the preparation and testing is the same code. Because I'm usually getting asked by clients, what do we need to use, GPT-2 or 3 or this or that? And open source, you have NewX and others, and how much reuse we're going to have from whatever we're building. So you can have a lot of reuse, even when you change the models. And again, there's also other challenges around the continuous deployment. Once you have the model, how do you put it in production in a non-destructive way? And how do you add observability and governance to the flow? So this is part of the solutions that we've added with MLRun. Is all the automation, all the auto scaling is built in, as I'll show you in the demo. We're training. It will spread across multiple machines with similar definitions. It has automated integration with CI/CD, with different engines, and automated observability. So now let's move to the serving pipeline, serving workflow. This is again an example of a serving pipeline for an LLM. So we get some requests, some question. We need to process it, parse it, etc. The next thing we need to do, in many cases, is do some enrichment. Maybe we need to bring another document for prompt engineering. Maybe we need to do embedding. So we need to take the user request and add some additional context to it and feed it into the model. Again, potentially doing some prompt engineering. Then we drive it into the foundation model. After we drive it into the foundation model, again, maybe some post-processing, change the text, format the text, validate that we don't have toxic answers, and so on, and respond to the user. In addition, everything that happens here, we want to throw it into a monitoring system that examines the request and response, and then we can run various jobs for analyzing it. Did we have good answers? Maybe we can use it for the reinforced learning. We have all the requests and answers, and we have human laborers that say if these are good requests and answers, and feeding that data later on into the training. So the challenge that we have here, again, is integrating all this stack of application logic, business logic, the data engineering logic, the model logic. There are a lot of issues around performance and scale. Again, fitting the models into the memory. We may need multiple GPUs. But some of the challenges we had in preparing the demo, we went to Amazon and said we need 4 GPU nodes with A100. We didn't get. It's like maybe there's an allocation issue now. Everyone tries out LLM. So you see there are some challenges are even at the infrastructure-based level getting access to those nodes with GPUs. How do you do real-time validation and monitoring? Say, okay, we have a toxic answer. We want to block it, replace it with some pre-formatted text. So we need to do it in the application pipeline. We don't want to do it afterwards. And continuous deployment. Canaries, how do we switch from one model to another? One of the things that we're doing is we're doing canary for the entire pipeline. If we're just doing canary for the model itself, you may have a problem because some of the logic before and after the model may change with the version of the model. So this is just one example. And so what we'll show you is how we do rapid deployment of the real-time pipelines using the real-time graph technology. Everything there is elastic, including GPU as a service support, automated model data monitoring. Again, all the things that happen in that pipeline getting tracked automatically and used for various applications. And another thing which is important when we're talking about MLOps is version control and also collaboration. So what I'm trying to educate more and more people, also from my book and other lectures, is start the generating practices of software engineering in your machine learning stack. So you may have different personas working on a project. So maybe the data scientist, he builds some Jupyter notebooks and some functions for the training or some testing. Maybe the data engineer builds some functions for manipulating data and transformations and features for the feature store. Or the MLOps engineer builds workflows for automation and maybe additional testing code and so on. So they all need to push the results into a version Git repository. They can also do interactive development, which is very important. A lot of people don't like pushing to Git and waiting for Jenkins to do its work and only then seeing the results. A lot of people want the ability to directly interact with a cluster, run jobs, get the response, and then push their version into the Git. Once they do, you want to apply hooks in your CI system that will automatically do things like static testing and maybe some other tests. And once all the tests pass, you want to be able to deploy a certain version into one of the clusters. In many cases, there's more than one cluster. There's like a development cluster, a staging cluster, and a production cluster. Because on a staging cluster, you deploy a full version, you run tests with extensive amount of data, you see that it works, and then you're saying, okay, now let's move it to production. And when you do production, you also do sort of a rolling upgrade of the version. But essentially putting everything in Git, including some metadata and configuration, allows us to just load it into a cluster and start running it and collecting all the telemetry. So this is how to manage the lifecycle. And I'm going to show you a nice demo that we built with my team of doing fine-tuning of a machine learning model using GPT-2. And this is like the training pipeline. What it's doing, the first step is scraping a website, in this case the MLOps documentation, so knows a lot about MLOps. And then doing some data pre-processing, doing the training, evaluation, and deployment of the model. Once we do the deployment, we're doing additional testing. So all that pipeline will show how we build it and run it. And again, you get all of those different results. It integrates well with Git, GitHub Actions, Jenkins, and so on. And you could actually use this as the MLRun marketplace to use those components. You don't need to develop those. Another nice thing about MLRun is those functions could be elastic. So the training function is using Corvid and MPI to essentially distribute the training job across multiple GPUs. And then once we'll do the training pipeline, we'll show you how we build the real-time serving pipeline. And this serving pipeline, again, not too complicated. It has some pre-processing, the model scoring, some post-processing, and even a toxic language detector. Filter. Describing this pipeline is about a few lines of Python code. Then you could essentially ask questions using your model in the development environment. You don't have to go to build things on the cluster. When you feel it's done, one command, one API call, and it's deployed on the real system. So this is that. And the last thing, I'm not sure I'll get to demo it, but the model monitoring, the nice thing here, we connect all the X and Y data from production and training, and then you can apply different applications, whether it's for drift or accuracy or risk or bias. There's also a way to create custom monitors, which will probably be more applicable to NLP workloads. So let's move into demo. So I have two notebooks here. One notebook is, sorry. So I have two notebooks in my system. I have two notebooks. One is for serving, one is for training. And what we'll see, let's start with the serving, but this time what I'm serving is the model which is the baseline model, without the fine tuning, without the training. Just I want to show you that it's sort of a dumb model, doesn't know anything about MLOps. So, you know, what we're defining here is an MLRun project, and then we're defining the pipeline that we've seen here, the data processing, the GPT-2 model, the post-processing, and the toxic analyzer. Because there are built-in classes in MLRun for a lot of those things, you don't even need to define to implement code. The only code you need to implement is for the pre-processing and the post-processing, and which sits here in the source directory. But again, very naive code for pre and post-processing. We're using a component for Hugging Face integration. So essentially, we know how to load a Hugging Face GPT model, the GPT-2 model, and use it. So once we build this pipeline, the next thing that we want to do is save the function in the project, and we can create a simulator. This mock server is essentially creating a simulator of the serving pipeline. So we don't have to go deploy it on a cluster. We can just go and debug and put breakpoint. And here we're just doing some tests with the simulator, and we see it doesn't know much about MLRun or MLOps. And so pretty dumb responses. Okay, machine learning. It's machine learning. So just to show you, I built the pipeline, but it doesn't have a lot of interesting thing. And I can deploy it as an endpoint in the cluster by just saying deploy. And this will essentially build the containers, builds the pipelines, builds the API gateways, the ruling algorithms, all that is fully automated. And if we want, we can even create like a G-radio front end in front of that function, so we can have a nice UI. So this is sort of the serving pipeline. But what we want to do is now build the training flow. So in the training flow, we have several functions. We have the data collection, which essentially we give it the URL, and it does scraping to grab all the HTML pages and convert them to text. The processing essentially turns it into tokens and does some other cleaning on the data. Then we have the training flow that takes the tokens and builds the fine-tuned model. And the serving and testing are, we want to deploy the serving pipeline and we want to test the results. So we build a multi-stage pipeline with all of that. So the pipeline code is actually in the workflow. It's also using Kubeflow. If you're familiar with that, is the underlying engine to run this pipeline, and it has those different functions. I'm just saying, what is the function? What are the parameters going into the function? For example, I want to do scraping. What's the URL of the website I'm scraping? And so on. So and here I'm doing the training, and I'm using MPI, sort of the distributed training for running the training. So when I'm just saying run the workflow, we're giving it some inputs. Again, going to budget log for MLOps, for the data, giving the model name, and so on. Part of the arguments of my pipeline. What I'll see is actually starting to run the pipeline. I can see the pipeline interactively on the notebook, or I can also open the MLRun UI and actually see the pipeline. I'm not going to run it because it takes an hour, so we don't have so much time. But you can see it has all those different steps. For every step, you know, whether it's the scraping or data processing or training, you can see what were the parameters used for the run, what were the, you know, all the runtime attributes, what are the outputs. For example, for the training, we have some loss curve, and so on. And then we're doing the deployment and testing, and each step we can go and monitor in real time how it's progressing. You see all this data, all those charts are collected automatically. They don't even need to do anything. It examines the outputs of every job automatically, and based on that, building the visualization and lineage graph and all that. So no need for instrumentation. Okay, so this, I can also visualize it in Jupyter and see the progress of my job. And the nice thing, you get a report. By the way, if you're working with Git, this report goes into your pull request message. And you can see what was the accuracy, what were the results of every testing step, and so on. And again, in the user interface, you can track the flow of the graph. And this is something that we captured during the run of the training. You can see that this specific job, when we open pods, because it's all running on Kubernetes, you see that the training job is actually using, I think it's like 8 or 9 workloads. It's actually 8 containers, each one with its own GPUs that are running the training. Now you, as a guy who wrote the code, you don't need to know anything about it, because what MLRun knows how to do through hooks in TensorFlow or PyTorch, it knows how to distribute the workload. So you don't need to do anything about it. It will automatically distribute the workload to multiple GPUs, which is really powerful, and you can see the loss curve as one of the artifacts, and so on. So now we'll take the new model that we fine-tuned, and we're going to ask the same kind of questions we had before. So what is MLRun? In this case, now you see we're getting very accurate results. One of the things you can see here, it's not as nice as ChatGPT, because ChatGPT will take the output and essentially format it after. So this is part of the post-processing. We may need to add some more logic to do some rich text formatting and so on. But you see that the answer is pretty accurate. So I'm thrilled about it. By the way, we worked on it for 2-3 days. This is all the amount of time taken, and this is like what is machine learning. And again, we get something pretty nice, you know, after 1 hour training with GPT-2, which is not too sophisticated, and about 10-20 pages of documentation. You get something pretty nice. And again, you can tune it, and you could add more testing, and so on. And then, again, we can build a G-radio and have something more interactive against the model. Okay. So with that, you see how we can very easily take some data of like 20 HTML pages, feed them into the model, do fine-tuning, additional testing, and so on, build the model into production with very limited amount of code, and deploy a model that now works with your own data. And again, we may go and enhance it, add more filters and things to mitigate the risk and improve the quality for tuning. But all the flow is, I don't need to have full engineering skills. I just use some bit of Python and deploy anything to a very scalable system. Yes?
You get a price predictor before you run it, and so you, because even if it's in an hour, if it's on 100,000 nodes, it might be.
No, so it's only, we use here 4 nodes. Part of the problem, we didn't manage to get more than 4.
Okay. Okay.
And it wasn't too expensive. Okay. Part of the way that it works is auto scales. It's through the Kubernetes scheduler to increase and reduce the number of virtual machines used. So once the job with the GPU finishes, it decommissions the virtual machine. So part of it, and this is really the reason why we managed to lower costs significantly, because it scales to do the job, and then it sort of shrinks to 0. By the way, on the training and the serving as well. The serving is using an engine called Nucleo, which is an open source serverless framework we developed, very high performance, which is also auto scaling on the GPU side. Yep.
Is there any significant difference between training on one node and like multiple nodes?
So part of the challenge is the LLM size itself, because some models, again, even within the different families, you'll have different sizes of models. Again, GPU may have 16 or a gig of RAM, or maybe more, depending on the type of GPU. Here we actually use 4 Teslas, because we didn't manage to get A100, so it's not too expensive. But if you have a model which is like 100 gig or 200 gig, and for the training you actually need more memory, like 3 times more memory, etc. So you have to more nodes. Okay, so again, like if you think about GPT-4, 25,000 of those. But for the fine tuning, you don't need so much. Like you don't need to train for 3 months. You know, maybe an hour or so, depending again on the amount of data that you're using for the fine tuning. Yep.
How can you use your own data without training?
Without training?
Document. You have document from a company, you want to use it, you want to do a training.
So that's what I call the prompt engineering. You can also do that with ChatGPT. You feed it with document and you say, summarize this document. So the way that people use it is they use like a vector database to search the relevant document based on certain embeddings and then feed it into the prompt. And again, it has the limitation I mentioned, that the amount of data that you can put in a prompt is limited to about 1,000 or 2,000, I think, words. So, yep.
I'm wondering from Iguazio's perspective, what is the typical training size, and how do you guys define the training loss?
So, first here we didn't do too many epochs, again, just because time and cost, etc. So, but you could just look at the loss curves and the accuracy curves to see that they're getting to something decent. You may need like a couple of dozen epochs or something, but it really depends on the amount of data and type of data. But again, the fine tuning is not that expensive. Definitely compared to building your own model. Again, 1 hour of few GPUs is not extremely expensive. So I'm less concerned over that. Yeah.
It seemed like a lot of the steps you were describing for like putting these AI models into production are very similar to a sort of standard MLOps workflow. Are there any AI specific steps?
You mean LLM specific?
LLM specific steps.
So a lot of things in MLOps will be around structured data in most cases, pandas and one-hot encodings, etc. Here it's not relevant, so it's more things around embeddings and tokenization, and even text processing is slightly different, like cleansing data. We use documentation, may have HTML tags that you want to remove, etc. So there are more aspects around this, and also in the validation and testing, it's more complicated, and on the monitoring, it's more complicated. Because if you do drift analysis, what are you doing? You're essentially doing histogram analysis on X and Y for the training and the survey, and you're comparing the two histograms, and then you know that you have a drift. How do you do it in LLM? It's words. Okay, so you need to do some text analysis that will convert it into some numeric values, or maybe do some clustering or some other type of logic to compare the training or the expected results with the actual results. So there's more innovation there. There are some packages, open source packages that could be used for that, but it's not your traditional, histogram comparison stuff. Yep.
Is there a reason I'm still not understanding MLOps versus DevOps, looking at a tool that can basically I can model the ML sequences, generate a script for CI/CD, and then that be basically at that point does that not just become DevOps?
So that's a great question. I'm covering a lot of it in also my book, etc. But if you think about DevOps, okay, you have Jenkins that sort of runs a bunch of jobs, you have a bunch of reports. It doesn't do a few things. First, it doesn't track experiments, okay? It doesn't have the notion of what's a model. Like part of what happens here behind the scene, a model is getting registered. A model register is not just taking the pickle file, it's also taking samples of the data set to go along with it. It's generating schemas for the data set, so later on when we're doing the survey, we'll be able to do things like monitoring and validations and so on. So there's a lot of metadata that's generated for you that if you just run Jenkins and launch a job, you will not get it. There's a lot of context around data like very large data that moves across the pipeline. So how do you sort of use some shared object store or something to move things around very large data objects, or, database connections across the pipeline, usually not addressed by DevOps. There are other things like distributed computing. If you run just again Jenkins, GitHub Actions, you launch a job, you launch a container. Here we need to launch 20 containers with GPUs and Elastic Assets and things like that. So you may want to use your Jenkins or GitHub Action as a trigger to launch something on an MLOps platform that know how to deal with all those aspects of elastic processing, data movement and data versioning and data lineage, metadata, which is more specific to MLOps, and you can just use the tools. You can use the tools and then add lots of your own blue logic. We've seen some clients doing it, but eventually they surrender and they start doing it the right way.
So,
Does it answer your question?
Yep, thank you.
is human in the loop feedback built into this platform, or if not, how are
So
clients
because all this stuff is getting monitored automatically back into the feature store, it essentially creates feature sets for production. And then you could just go and create another application. It goes to the feature store, fetches the data set, does annotation, and returns it back. And then you're retraining, basically. So it doesn't do all the work for you, but it provides all the foundations that you just need to put the logic of your labeling and so on. Any more questions? Yes?
Sorry, sir, we have another
We're
speaker
done?
incoming. Yeah. Thank you so much.
Thank you.